This is a story about electrifying our 100-year-old home. We purchased this 1,200 square foot Spanish Revival home on the California Monterey Peninsula in 2019. It was built in the 1920s and went through a major renovation in 2008 that included the elimination of the utility room and locating the gas furnace in the crawl space and placing a tankless natural gas water heater on an outside wall. Some of our goals at the time included the elimination of our household greenhouse gases and pollution emissions and reducing our overall energy cost. It was a good candidate for this because it already had modern electrical, windows, and insulation, so it was relatively energy efficient for a 100-year-old home. It also had an unobstructed southern exposure for a sizable solar array. If you look closely, you can see one of the solar panels peeking over the flat roof section. Our first step toward our goal of reducing our greenhouse gas and pollution emissions was to subscribe to 100% renewable electricity from our local community choice aggregator now known as Central Coast Community Energy. That was an easy step, but it left us with all the emissions from our natural gas we were burning and leaking into the air from our heating and cooking appliances. To reduce our use of energy, we of course did the easy things like switching out our light bulbs to LEDs and using a programmable thermostat. We also needed a new clothes washer. The electric dryer that came with the house was old and an energy hog. And with limited space in the garage, we opted for an ultra-efficient combination heat pump dryer and washer. This single full-size unit washes the clothes and then dries them all in one step. Ventless heat pump dryer technology is very common in many other countries, especially in Europe. Because of lower heat, they are very gentle to fabrics. Their only disadvantage is that drying takes longer. With this combination unit, you also can't double up washing one load while you're drying another at the same time. But for two people, this isn't a problem, and it's easy to get used to. The other advantage is that it runs on a standard 120 volt outlet. This freed up the 240 volt 30 amp outlet in our garage for our EV charger. And since this dryer uses a heat pump, and we will also be talking about them for house and water heating, this is a good time to talk about the basic principle behind heat pumps. Heat pumps are not new. Air conditioners and refrigerators are common examples. A heat pump uses a closed system containing a refrigerant, which is a substance that evaporates and condenses under the desired temperature and pressure conditions within the closed system. The process begins when the pressurized liquid refrigerant is released into a low-pressure area in the evaporator coil, causing the refrigerant to cool. As it passes through the evaporator, it absorbs heat from the surrounding environment, causing it to warm. In a refrigerator, the evaporator is the coil inside the refrigerator. A pump compresses the heated gas into the condenser, making it a hot, high-pressure gas. And as it passes through the condenser, it transfers the heat to the surrounding environment, causing the cooled refrigerant to condense and returning it to a high-pressure liquid. This cycle continues as long as the compressor is running. Heat pumps do not create heat. They merely move heat from one space to another. Moving this heat using electricity to operate a compressor is much more energy efficient than creating heat either through combustion, such as with natural gas, or through electrical resistance heating used in conventional electric water heaters and furnaces. Heat pumps have been the go-to technology for cooling applications for a long time, but for heating, not so much. They cost more than conventional furnaces and water heaters, but the savings from heating with heat pumps are over time in lowered energy costs, as they can use 1/3 or less energy. The desire to eliminate greenhouse gas emissions and other harmful pollution from using natural gas is increasing interest in heat pump technology. We are surrounded by enormous amounts of heat in our atmosphere, water, and land. Here we see an air source heat pump on the left and a ground source heat pump on the right that draws its heat out of the ground. The decision to install solar was a simple financial choice because it was expected to yield a payback within 7 years and substantial energy cost savings for 20 plus years. As we began looking at the project, we learned that we also needed a new roof. Here we see the finished installation with the panels securely attached to the roof framing. We also upgraded our electrical service to 200 amps to accommodate additional panel outlets for future electric space and water heating and an electric range. We used the information from our first 9 months after buying the house on our electric bills to help us size the array. Now, more than 2 years later, we have good information that tells us how our electric billing is offset through net metering and what our costs will be looking forward. Next on our path to electrification was replacing the gas range that came with the house. It was functional, but was tired, had no warming drawer, was hard to clean, and our indoor air quality monitors registered high when it was used. Our primary motivation was to eliminate our exposure to the harmful emissions. You have no doubt heard the controversy in the news media lately about cooking with gas. We selected this LG induction cooktop range with convection oven and a warming drawer. This was our first experience with induction cooking, although we did have friends who loved theirs. Rather than heating the pan and much of the surrounding air from combustion of a fuel or using an electric heating coil, induction cooking heats the pan using an oscillating magnetic field to excite the molecules in the pan. This uses much less energy and introduces much less heat and pollution into the kitchen. We did have a few non-magnetic pans that we couldn't use. Here you see it installed along with the overhead microwave with a 400 CFM exterior vented fan, which is adequate for induction cooking because of the lower emissions and lower introduction of heat into the room. Cooking is fast, precise, and it's a whole lot safer with no open flame or hot cooking surface. And the induction turns off automatically when there is no pan present. The surface is easy to clean. We use some silicone pads under the pans to protect it from scuffing. With no methane to leak and no combustion emissions, our kitchen air quality is much better. We have no complaints. It's especially fast at boiling water in about 1/2 the time of a gas burner. Although I've heard complaints with wok cooking, there are now induction wok cookware and cooktops that carry the heat high up along the side of the pan. With over 2 years of detailed history about our use of natural gas and electricity production and use, we had the ability to estimate how much electricity we would need to replace our gas furnace and water heater. As you will soon see, it also provides us with the ability to model different scenarios looking forward. Here is an example of solar production on a typical March day with some intermittent clouds. The Solar Production Database provides excellent analysis and reporting. This Bryant heat pump was installed just before the oppressive temperatures of a heat wave that stalled over California in September of 2022. We hadn't really expected to need air conditioning here just a 1/4 mile from Monterey Bay, but we did use it that week. We had no operational reason to switch out our gas furnace or our water heater because they were both working fine and probably had 5 to 10 years of life left in them. We were motivated to eliminate our emissions and reduce our utility cost. This Wi-Fi connected Nest thermostat was also installed. The air handler part of the system, which is contains the circulation fan, replaced the furnace under our house in the crawl space and connected directly to the existing duct system. Because we already had capacity for the additional power and circuit breakers in our main breaker box, we just had to add the new 240 volt 30 amp circuit. The records we were keeping allowed us to size the heat pump and to estimate our electricity use going forward based on the amount of heat the old furnace had been generating and the energy efficiency of the old furnace compared to the heat pump. The first thing we noticed was that the variable speed air handler circulation fan was much quieter than the old furnace. It also took a little longer to heat the house in the morning. As it was explained to me, the temperature of the hot air coming out of the air handler isn't as hot as that coming out of a gas furnace, so it takes longer. To adjust, we simply set the thermostat to start a little earlier, and because it doesn't awaken us when it starts like the gas furnace did, we now sleep better and have a warmer house when we get up. We've been very pleased with it. This illustration shows the heating cycle that adds heat to the house. They have a reversing valve that reverses the process to remove heat from the house. Although tankless gas water heaters work well, like all gas-burning appliances, they emit CO2 and other harmful pollution. They are especially bad at leaking natural gas, which is a very potent greenhouse gas. Every time they ignite, they release a puff of methane, including when someone mistakenly turns on hot water for just a moment. This happens a lot, especially with single-handle water faucets that mix cold and hot. Ours also circulated hot water in the hot water line, so the burner would turn on or off every so often, even when there was no hot water being used. All of this extra water heating and leaking of gas significantly reduces their advertised high energy efficiency. Here we see from the Stanford study that nearly 1% of the natural gas delivered to these units is emitted unburned directly into the atmosphere. This is significant because when methane is released, it is 100 times more potent than CO2 as a heat-trapping greenhouse gas. I could smell gas whenever I was near it as it ignited. Switching out our tankless gas water heater for an electric water heater posed a few challenges. We ruled out a tankless electric water heater because they require an enormous amount of instant electricity, and they aren't at all efficient. Another option would be an inefficient conventional electric water heater with a tank that uses resistance heating. Because our utility room had been eliminated way back in 2008 when they did the remodel, we also didn't have any room for an indoor water tank. That left us looking for a heat pump water heater and a tank for an outside installation. This Sanko system by Sanden is unique in that it uses carbon dioxide as its refrigerant and a well-insulated stainless steel tank suitable for inside or outside use. This is not new technology. They've been used extensively in Japan and Australia for over a decade. They are very energy efficient and durable. It required a dedicated 240 volt 15 amp circuit. We had eliminated our use of natural gas, but we weren't done just yet. Based on our increased electricity use for the heat pumps, we needed about 10 more kilowatt hours of average daily solar production. This required some more solar panels. Let's look forward using our detailed energy use data to model what our annual costs and emissions would be under several scenarios in the next year. If we had stopped at the heat pump, washer, dryer, and induction range but did nothing else besides subscribing to our community choice electricity energy supplier, our expected household energy costs and emissions would have looked like this in the next 12 months at current electric and natural gas prices. You can see that our costs for natural gas, for space and water heating, plus household electricity, plus EV charging for 15,000 miles that we drive annually, would total $3,446. Our greenhouse gas emissions, which includes a factor for leaked natural gas, would be substantial at over 7,400 pounds per year. And we and our neighbors would all be breathing our pollution. With all we've done to electrify everything, but without installing the solar, it would have looked like this. We would have achieved our goals of eliminating our CO2 and other harmful pollution, but out-of-pocket cost would have been close to the same. Actual cost, which includes the substantial cost of our greenhouse gas and air pollution that we would have been putting on our neighbors and future generations to pay if we had continued with natural gas, would be much lower. So electrifying everything is significantly better even if out-of-pocket cost is close to the same. Lowering our out-of-pocket cost is where solar comes in. Solar is a long-term investment, and the costs and savings associated with solar should be measured over the long term. It is a good hedge against increased electricity prices in the future. But looking into the future, of course, involves speculation. So how to estimate what is going to happen with electricity prices in the next 20 years? In the past 20 years, the annual inflation rate for electricity has been 3.15%, which is slightly higher than the cost of living rate of 2.5% during this same period. We have recently experienced significant increases in both natural gas and electricity, mostly tied to global price increases for natural gas. And the future will require considerable capital investments to electrify everything, including transportation, which will increase the amount of electricity we must generate by 1/3, for all of our heating, manufacturing, and other uses of fossil fuels. To transition to 100% renewable electricity generation and the required energy storage will also involve considerable capital investments. And then, of course, we need to harden and modernize our electric grid. We need to underground our electric lines in vulnerable wildfire areas. We need microgrids that are more stable so we don't have all the blackouts that we experience. On the positive side, renewable electricity is already lower than all other forms of electricity generation. So we have a mix of inflationary and lowering cost factors to consider. But to be conservative in the analysis that I'm going to proceed with, I'm going to use the same annual electric price inflation rate of 3.15% that we have experienced over the past 20 years. Here we will look at our electricity cost going forward. Shown is the base period from the previous slide with our fully electrified house without solar. It also shows a 20-year total cost of electricity based on an electricity inflation rate of 3.15%. Based on our electricity generation and use, we know that moving forward with solar but without any electric storage, 70% of the electricity we generate will be exchanged with our utility, meaning we send most of it to the utility only to later draw it back from the utility when the sun isn't shining or when we are demanding more than we are producing. Our solar installation is governed under California's Net Energy Metering 2.0 rules. Under these rules, the electricity we exchange with the utility is priced at retail. And because our solar array is sized to generate about the same electricity that we expect to use, and we are charged and credited at the same price, we pay nothing for the electricity we exchange. The $380 utility cost shown is basically a connection fee. This means our solar array should save us $3,026 in the next year, and over the next 20 years, using the same 3.15% annual electricity inflation rate, our utility costs should total $10,368, saving us $82,562 in utility costs over the next 20 years compared to not having any solar. This next projection shows what our costs would be under the new Net Energy Metering 3.0 rules recently passed by the California Public Utility Commission for residential solar installations after April 2023. This reduces the credit for electricity supplied to the grid by 75%. Using our standard pricing, we would pay 33 cents per kilowatt hour for electricity we draw from the grid and be credited at only 8.25 cents per kilowatt hour for electricity we supply to the grid. The justification for this is that it's closer to what utilities can buy electricity for on the wholesale market during peak solar hours when solar-generated electricity is abundant. You can see why Net Energy Metering 3.0 is often described as a home solar killer, with the savings and return reduced so much. But is it a solar killer? Not really. It does mean we'll need to change some of our behavior and how we configure home solar installations moving forward. Before looking at these changes, let's first consider why so much of our solar production has been exchanged with the utility. There are several good reasons why we send so much energy to the grid, only to later pull it all back. First, we have 5 consecutive months when the solar generated is significantly more than what we use. And the amount of storage required to store all this accumulated excess would be prohibitive. Using a level 2 EV car charger is another cause of high utility supplied electricity. Level 2 chargers draw electricity at a rate that exceeds what a home solar array generates, so the balance is drawn from the grid. And all nighttime charging will come from the grid. The alternative is to use a level 1 charger during daylight hours. Of course, this doesn't work if your car isn't at home during the day. And the other reason is that without storage, any electricity we use when the sun isn't shining will have to come from the grid. We can, of course, change our behavior to avoid some of this, like avoiding our use of washing machines or not running the furnace after the sun goes down, but some of these drastic measures aren't practical. This analysis will show several scenarios under Net Energy Metering 3.0 that could significantly reduce the portion of our generated electricity that is exchanged. We will still compare them to the same base period from the previous slide with our fully electrified house without solar. The first continues without any storage, but adjusts our EV car charging and other electricity use to exchange only 40%. We could switch to a level 1 charger to manually manage our draw for EV charging, or we could install a smart car charger that can be set to only charge the car using excess solar-generated electricity. Other manual measures, like avoiding the use of appliances or hot water when the sun isn't shining, could improve this even further. This scenario without any battery storage would also leave us vulnerable to those power outages we occasionally experience. Our annual utility cost would be more, but we would still be saving a considerable sum with a payback in about 10 years. Now, this doesn't work for many because their EV isn't at home during the day, and people who don't have an EV will find the 40% exchange goal much easier to achieve. The next scenario combines solar storage with smart EV charging to achieve only a 20% exchange. The investment goes up, but so does the 20-year savings. And the last scenario with battery storage would apply to EV owners that can't charge their car at home during the day and instead revert to level 2 charging mostly at night, with 55% of the solar exchanged. Net Energy Metering 3.0 still provides a very good return. And if the price of electricity goes up more than the historical rate of 3.15% per year, the return is even better for all of these situations. So there you have it, our story about this old electric house. But before I close, let's review what all of this has accomplished. We eliminated all of our greenhouse gas and pollution emissions from our household and those generated upstream by those who supply us with energy. We no longer contribute to the wealth and power of autocratic petrostates and the stranglehold they and their fossil fuel industry partners have on the global economy. Instead, we are using energy that falls freely on our home and supporting renewable energy manufacturers, local contractors, and their workers who are helping us to make our world a better place. We have lowered our costs for household energy with plenty of savings to recoup our investment and to protect us from energy inflation. Our home is more comfortable and better for our health and safety and that of our neighbors. And we also hope we have inspired others to follow in our footsteps. Climate change is real and of our collective making. The United States is responsible for more of the greenhouse gases now in the atmosphere than any other nation. 25% of the accumulated greenhouse gases from only 4% of the global population. The world must soon stop using nearly all fossil fuels if we are to avoid the worst of the climate destabilization that is already producing unprecedented weather extremes and rising seas that are disrupting the lives of millions around the world. The world will not likely act soon enough if the United States doesn't show the way. And although individual actions we take to eliminate our personal greenhouse gas emissions are important, these alone will not be enough. We need government leaders committed to making it happen very soon across our entire economy. Please join those who are using their voices, their votes, and choices to fight the climate crisis, because your world depends on it. Thank you for your time and attention. My book, The Sustainable Way, was published in 2016. The subtitle, Straight Talk About Global Warming, What Causes It, Who Denies It, and the Common Sense Transition to Renewable Energy, explains what it's all about. It's a plain-spoken 50-page booklet, a comprehensive source of information covering the science, economics, politics, and technology relating to global warming and renewable energy, and it's easy to find. If you would like to learn more about why we made the switch to zero-emission vehicles, you can view my presentation about electrifying transportation at this address.